Okay, so I'll be taking two examples the um for this chapter, and we have the first example as a particle moves in space so that at time t its position is stated or started as x equals to 3t plus 3, y equals to t squared plus 2t, z equals to t cubed plus 3t squared. Find the component of its velocity and acceleration in direction of the vector 2i plus 3j plus 4k when t equals to 1. So here we are given a parametric equation x in form of the parameters x, y, and z, and from the name parametric, that is, we are given the position of the object on a curve. We said it moves in space in form of like the three parameters, which is the x, y, and z components. So for question 1, we start by actually forming our displacement vector. So to actually get displacement, we combine the components. So for the x parameter goes with the I component, the y goes with the j component, and the z goes with the k component. So we have our vector r, which represents the displacement or position of the object. You can call the position vector now as 3t plus 3i plus t squared plus 2tj plus t cubed plus 3t squared k. Okay, so now we said we should find the component of velocity and acceleration in direction of this. So we know that velocity is displacement over time, which is actually the gradient of displacement with time. So that is dr dt, and our acceleration a is dv dt. So invariably we can actually say that a equals to d square r dt square. So for our v now, we have to actually differentiate the vector, and from our previous exercise I think we should know how to differentiate vectors now. So dr dt would give 3i plus 2t plus 2j plus 3t square plus 6tk, and that is our velocity v. So now we also want to get the acceleration, which is d square r dt square. So we differentiate this again, and this one becomes 0 automatically because it's constant. Then we have 2j plus 6t plus 6k. Now no, they said when t equals 1, so that's what we're going to do here. So when t equals 1, we know v equals 3i plus 2 into 1 plus 2 1 into j plus 3 to 1 square plus 6 into 1 k. So we have 3i plus 4j, which is 2 plus 2, so let's just make that 4j plus this is 3 plus 6 plus 9k, and that is the component of our velocity in this at when t equals 1. So for acceleration we have 2j plus 6 into 1 plus 6k, and that evaluates to 6 plus 6, which is 12k. But they said in the direction of the vector this. So what we need to do to get the vector in the direction of the velocity and velocity in the direction of the given vector is to actually multiply the components of velocity and acceleration by the unit vector of this. So the first thing we have to do is to actually get the unit vector. So let's call this vector vector A. Vector A is 2i plus 3j plus 4k. And to get the unit vector, we said the unit vector of A equals A over the magnitude of A. So to get the magnitude of A, we have square root of 2 square plus 3 square plus 4 square, and then invariably gives us 4 plus 9 plus 16, which is root 29. And we can have a unit vector of A. Let's call that unit vector I now. I equals A 2I plus 3J plus 4K all over root 29. Now, like I said earlier, to get the components in the direction of this vector, we just multiply. So that means our answer will just be V equals to, let's call that VI, because that's in the direction of I now, equals to V times the unit vector of A here, which is I. So this is VA in the direction of A, and then in our acceleration, which is small a, in the direction of A, is going to be A times the unit vector. Note, this is not cross product or just normal multiplication. We can really still say it's a dot product here. Dot product. And now all we need to do is to actually multiply. So for velocity in direction of the vector A, we have our velocity is given as 3I plus 4J plus 9K dot 2I plus 3J plus 4K. In direction, velocity in direction of A, we have VI dot I, which we have the velocity vector multiplied by the unit vector, which is this over root 29. Then we can factorize out our root 29, and we have this multiplied by this, or the dot product of these two vectors. And when we evaluate that, we have 3I times 2I, and that should give us 6. 4J times 3J, that is 12, and 9K times 4K, that is 36. So we have 1 over 29 into 6 plus 12, which is 18, plus 36, which is 54. And this 54 over root 29. Okay, then for the component of the acceleration in the direction of the vector A, so that we said that is A, then multiply the component, which is 2J plus 12K multiplied by the unit vector I plus 3J plus 4K all over root 29. And we do the same factorization, and we have 2J plus 12K, we have 2I plus 3J plus 4K. So now we have 1 over root 29. So here we don't have an I component, so that's basically 0I, and 0I times 2I will give us 0. 2J plus 3J will give us 6, and times, not plus, multiplied by 3J or dot, and we have 12k dot 4k would give us 48, and that becomes 1 over 16 to 54, which is 54 over root 29. So now to question 2. Question 2 says find the unit tangent vector at the point 2, 0, pi for the curve with parametric equation x equals to 2 sine theta, y equals to 3 cos theta, and z equals to 2 theta, where the point 2, 0, pi corresponds to theta equals pi over 2. So here we are told to find the unit tangent vector now. And what is unit tangent vector? Given a vector, let's call the vector b as ai plus bj plus ck. The unit tangent vector of b, begin, let's call the unit tangent vector u, because also a vector is the vector which is the derivative of the vector. Let's say the x depending on the depending on the dependent and independent variable here over the modulus of the derivative. So you get the derivative of the vector. We can put it simply as this: db over modulus of db. Now the derivative here taken is based on the independent variable. We'll see that in the example 2 here. So now we are given the parametric equation, and the first thing we have to do is actually get the position vector. So the position vector r is, like we did in the previous example, is 2 sine theta I plus 3 cos theta j plus 2 theta k. Now for this question we're given where the points 2, 0, pi correspond to. So we said it corresponds to pi over 2, but assuming we're not given, how do we get this? So all we need to do is to actually impute, in coordinates. Whenever they give us coordinates, we have x first, then y next, then z next. So we impute the x coordinates into the x equation, parametric equation, y coordinate into y parametric equation, and z coordinate to z parametric equation. So if we do that, the x parametric equation is x equals 2 sine theta, and the x coordinate is 2. So if we put 2 for x, 2 equals 2 sine theta. We're trying to find theta here now. So theta equals to sine theta, equals to 2 over 2, which equals 1. So to get theta, we have the sine inverse of 1, and the sine inverse of 1 is 90 degrees, and in radians format we have pi over 2 radians. Now when we are doing with cos, we actually deal with radians, so that is pi over 2. Now for the y parametric equation, we have y equals to 3 cos theta. So, and when we put in the y coordinate, which is 0 equals to 3 cos theta. So cos theta equals to 0 over 3, that is 0. So theta is the cos inverse of 0, and the cos inverse of 0 is usually 90 or 270. So that's basically pi over 2, or so 270 here should be 3 over 4 pi, if I'm right. So we can say that theta can be 90 or 270. Then z equals to 2 theta. So for the z coordinate now, the value for z in the coordinate is pi. So that is pi equals to 2 theta, and theta equals to pi over 2. So we can say that pi over 2 here, pi over 2 here, pi over, and that's why they said the point 2, 0, pi corresponds to pi over 2. So now back to our question, we have a position vector r given as this, and they said to get the unit tangent vector we have to get derivative of this position vector over the modulus or the magnitude of the derivative. So the first thing to do here is to get the derivative, which is the r d theta. Now this is our independent variable theta. So when we differentiate, we have differential of 2 sin theta will give us minus, sorry, not minus, 2 to give us 2 cos theta I. Because we are differentiating sin theta, 2 is a coefficient there. Then we have differentiating 3 cos theta, we have plus, put the plus there, minus, let's put our plus 3, minus sin theta g, and differentiating 2 theta, that will give us 2. Okay, remember, theta is an independent variable, just like having 2x. When you differentiate 2x, you have x 2. So when you differentiate theta, you get 2. So, and here, writing it, we have 2 cos theta I plus minus 3 sin theta j plus 2k. Now the next thing is to actually get the magnitude of this. The magnitude of this is square root of 2 cos theta square minus 3 sin plus minus 3 sin theta square plus 2 square. Okay, so now we can have this as square root of 4 cos square theta plus 9 sin square theta plus 4. And now we can then write our unit tangent vector. We said unit tangent vector of r, let's call that ur. We said it is the derivative of r with respect to theta all over the magnitude of that derivative. And writing that out, we have, this is the derivative here. To write that out, we have 2 cos theta I minus 3 sin theta j plus 2k all over our modulus, which is root 4 cos square theta plus 9 sin square theta plus 4. So we can leave our answer like this, but to make it simpler, we can actually just evaluate this. We can evaluate this. Okay, so we can simplify further by just factorizing out the root part as 1 over 4 cos square theta plus 9 sin square theta plus 4 dot 2 cos theta I minus 3 sin theta j plus 2k. So now we are forgetting something. We are supposed to put our theta equals to 2 pi into it, and we should have done that from the onset, but we can also still do that here. So once we put that in, we have 1 over root 4 cos pi over 2 square plus 9 sin pi over 2 square plus 4 dot, we have 2 cos pi over 2 I. So to next now we have minus 3 sin pi over 2 j plus 2k. So now we have 1 over, so square root of, so cos pi over 2, which is 0, cos 90, cos pi over 2 is going to give us 0, so that is 4 into 0 square plus 9 into sin pi over 2 is going to give us 1. No, note we are dealing with radians now here. So pi over 2 is same thing as 90 plus 4. And we have 2 cos pi over 2. So cos pi over 2 is 0 minus 3 sin pi over 2, which is 1 plus 2k. And we have this as, so this evaluates to 0 plus 9 plus 4 into, so this one also evaluates to 0 minus 3j plus 2k, and that is 1 over root 13 into minus 3j plus 2k. So note that